Okay, let's continue answering the ministry questions about RLC parallel circuit and oscillating circuit. Question number 1. An AC source of effective value, so this is the effective potential difference of the generator source, with a frequency of 1 megahertz is connected across a parallel combination of resistance 3000 Newton, this is R, an inductor of impedance 6000 and capacitor of impedance 2000 ohm. Calculate the value of the effective current of the circuit. So effective value of the current can be calculated by two ways. One of them, because R, XL and XC are given, you can calculate total impedance Z, and after that I effective will be V effective divided by total impedance. One of them is this. Second one is we can calculate electric currents for each electric current across the resistor, electric current across the capacitor and inductor. After that you can calculate total electric current. So I'm going to use the second method. Because it's parallel connected circuit, each potential difference across each device is going to be effective value of the source, which is 60 volt. One by one I am going to calculate electric currents. IR is the electric current of the resistor, which is V effective divided by R. So V effective is 60 divided by R, which is 3000. So let's calculate it. 60 divided by 3000, it's going to be 0.02 ampere. This is electric current across the resistor. Electric current across the coil, V effective divided by XL. So V effective again same because they are in parallel. XL is given as 6000. So 60 divided by 6000, which is 0.01 ampere. And next one is calculating effective electric current across the capacitor, V effective divided by XC. So V effective is 60 divided by XC is given as 2000. So 60 divided by 2000, result is 0.03. 0.03 ampere. Now I can calculate I total by the equation. I total is equal to IR squared plus IC minus IL square root. So I total equals root of IR is 0.02 squared plus IC is 0.03 minus IL is 0.01 squared square root. When you use this, you are going to get the answer 0.028 amperes. So A is going to be the correct answer. And let's continue with second question. An AC source is connected across a parallel combination of pure resistance and pure self-inductance and capacitance. It is a parallel circuit, and the angle of the phase difference between which of the following is 180. So in parallel, we know that potential differences are equal. So V is equal for each component, and we know IR is in phase with potential difference across the resistor, but electric current across the capacitor is leading the potential difference, and electric current across the coil is lags behind the potential difference. So angle between which and which is 180, of course IC and IL. So IC and IL is the correct answer. C is the correct answer. What about IR and IC? IR and IC, it's the 90 degree. IC and V also 90 degree. IL and V also 90 degree, but IL and IC, they are opposite in directions. So two vectors opposite in direction, angle between them is 180. Question number 3. A resonance circuit made up of an inductive coil, of variable coil, and a variable capacitor. So capacitance can be changed. Variable means that if the capacitance of the capacitor is lowered from 800 microfarad to 400 microfarad, by which factor frequency of the circuit changes? So as you see, C is decreasing. So I say that initial capacitance is C. So from 800 to 400, C changes to C over 2. And we know that frequency equation is 1 over 2 pi root of LC, which tells you that frequency is changing inversely proportional with root of C. So if C changes to C over 2, I am going to insert instead of C, C over 2. So this must change to this because it's inside the root. This root 2 flips up and it becomes root 2 divided by root C. So if I compare initial and final cases, I will observe that it is multiplied by root of 2. So F changes by root of 2. Answer is going to be root of 2. And also you can think this way, frequency and C are inversely proportional, but with the square root. If frequency if C decreases by 2, frequency must increase by what factor, which is the root of 2, because there is a root. Question number 4. A resonance circuit is made up of an inductive coil and variable resistor. If the capacitance of the capacitor is changed from 250 to 50, this time C changes to C over 5. So if frequency decreases by 5, frequency must increase by root of 5. Why? Because there is a root. Or mathematically, we can say that frequency changes by 1 over root C, because C changes C over 5. So instead of C, we can write C over 5. This 5, root 5 must flip to numerator. It will be root of 5 divided by root of C. I see that this one is multiplied by root of 5. So frequency must be multiplied by root of 5. Result is going to be root of 5f. So A is the correct answer. Question number 5. Which of the following is true when the circuit enters into resonance in an oscillating circuit? There are two types of oscillating circuit. One of them is the series, the other one is parallel. But choice C is correct for both series and parallel. A and B correct for none of them. That's why A and B can be cancelled directly. But D, the impedance of the circuit is maximum value. This is correct for only for parallel. In parallel oscillating circuit, impedance of the circuit Z gets maximum value. But in series, it gets minimum value. That's why D is not correct for all types of oscillating circuits. Just correct for parallel, not for series. But C, correct for both series and parallel. That's why correct answer in here is going to be C. And question number 6. Tuning the frequency of radio and television station at home to make a good reception of the broadcasting station is one of the applications of resonance, because if you are able to tune or pick up a signal from a radio station, frequency of your radio's oscillating circuit, LC circuit, and frequency of the radio station must be equal. When two systems are unequal in frequency, so those systems are called to be in resonance. So in this case, your radio and the radio station are in electrical resonance, so then you will start listening to radio. Question number 7. Which of the following is true for resonance circuits in series? This is a series one. As I said, C is correct for all types of connections, series and parallel oscillating circuits or resonating circuits. A and B is correct for none of them. But D, let's check D. Because it's a series connection, in series connection, VL and VC are equal, and potential difference across the capacitor and potential difference across the inductor must be equal. In this case, V total becomes only equal to VR, because VL and VC, because they are in opposite directions, we should subtract them. When you subtract them according to the V total equation, let's remember the V total equation. V total is equal to root of VR squared plus VL minus VC squared. So because these two are equal to 0, sum of them is equal to 0, second term 0, only VR squared remains, and when you got the root, we get V total is equal to VR. So V total is equal to VR is also a condition for series connections, parallel series resonating circuit, but this says that VR is greater than V total. This is not correct as well. So this is the correct answer. Question number 8. An AC circuit is connected across an RLC series. Again, it's a series resonating circuit. What is wrong? Which of the following is wrong in resonance? XL is equal to C. This is correct for all types of resonating circuit. F is equal to 1 over 2 pi root of LC is correct for both parallel and series resonating circuit. VL is equal to VC is only correct for series 1. Series oscillating circuit only. Z is less than R. This is correct for none of them, because we know that if XL and XC equal, which is the condition for both parallel and series resonating circuit, second term of the Z is going to be 0. Always Z is equal to R. For both series and parallel resonating circuits, Z is always equal to R. So this is incorrect for both of them. And both series and parallel resonating circuits, Z must be equal to R. That's why D is incorrect for both resonating circuit, also incorrect for series. Question number 9. An AC series circuit is made of an AC source and an inductive coil with a specific ohmic resistance. So we say that this is an impure coil, and a capacitor and capacitive impedance 62.8 ohm. So there is a impure coil with a resistance RL, and of course this impure coil must have an inductance XL, and also a capacitor is connected to this impure coil with C, and this is the frequency of the circuit is 100 Hz. If you know that omega L is equal to 1 over omega C, this is condition for resonance. Yeah, omega L is XL. 1 over omega C is XC, which this question tells you that XL is equal to XC. Yeah, system is in resonance. If in its resonance, their inductive impedance and capacitive impedance must be equal to each other. But capacitive impedance is given. Capacitive impedance is 62.8. 62.8 ohm is going to be the XC. And because XC and XL are equal, XL also must be equal to 62.8 ohm. Then I'm going to write the equation for XL. 2 pi f L is 62.8. Then I will calculate L. L is the question. Divide both sides by 2 pi f. Divide by 2 pi f. 2 pi f will simplify. L is going to be 62.8 divided by 2 pi is 6.28. F is given in the question as 100. So result is going to be, I think, 0.1 Henry is the correct answer. So C is the correct answer in here. And question number 10. The circuit shown in the figure is a resonating circuit. So what does it mean? In the resonating circuit, XL is equal to XC. So you don't need to count them. Z is equal to only R in this resonating circuit because XL is equal to XC for resonating circuits. Doesn't matter, it can be series or parallel. If effective potential difference of the source is 220 volt, yani V effective of the generator is 220 volt, and frequency of the generator is 60 Hertz. So the equation of the instantaneous current in the circuit, because it's a resonating circuit and only R has connected to generator. Why? Because XL is equal to XC. So you can think that this is a pure resistance circuit. So electric and potential difference are in phase. If electric and potential difference are in phase, and phase angle difference is 0 in a resonating circuit, all resonating circuit phase angle difference is 0, series or parallel, doesn't matter. So electric current potential difference are in phase. So electric current equation is I am sine omega t. I need to calculate what I am is. I need to calculate what omega is. After that, I will insert them. Omega, we know that 2 pi f, 2 pi times f is given in the question as 60. 2 pi times 60, which is 120 pi. Omega is 120 pi radian per second. So the D and A has 120 pi, so B and C cannot be correct. And also electric current maximum must be calculated. Effective value of the potential difference is given, effective value. So I should calculate maximum value because maximum current can be calculated only by maximum value of the potential difference. So effective value multiplied by root of 2 is going to be maximum potential difference, which is 220 times root of 2. So maximum is going to be, now let's calculate it by calculator. 220 multiplied by root of 2, it's going to be 311. Maximum potential difference is 311 volt. So now I can calculate maximum electric current. Maximum electric current is maximum potential difference divided by Z. Maximum potential difference 311. Because Z is equal to R, and our R is given in the question as 22. So 211 divided by 22, answer is 14.14. So maximum electric current is going to be 14.14. Then this is the correct answer. This is maximum current. 14.14 sine omega t is the equation for electric current. And question number 11, an AC series resonance circuit is made up of a source, a resistor of pure resistance, an inductor, inductive coil, and capacitor. So it's a series resonating circuit. In series circuit, we know that electric currents are equal. So I equal for all devices. We are in phase with the electric current, but VL is leading the electric current. VC lags behind the electric current. So the phase angle difference between total potential difference and current is what? Because in resonance circuit phase angle difference 0. Why? Because VL is equal to VC. In series resonance circuit, VL is equal to VC. In this case, these two cancel each other. So total potential difference becomes VR. And we know VR is in phase with electric current. That's why phase angle difference between the electric current and total potential difference becomes 0. So total potential difference, because VL is equal to VZ, total potential difference is only VR. And we all know that VR is in phase with electric current, so phase angle difference is 0. Or generally you can take that for all kinds of resonating circuits, phase angle difference is 0, parallel, all series, it doesn't matter. Question number 12, an inductive coil of resistance. So this is again not pure coil. So it has some resistance RL. An inductive impedance of 60, which is XL, is connected across an AC source of effective value 200 volt and frequency 60 Hz. Find the capacitance of the capacitor that should be connected in series to obtain the resonance. So there is an impure coil with a resistor RL and also an inductor XL. So, and also a capacitor. They are connected in series to a generator whose effective potential difference is 200 volt, whose frequency is 60 Hz. So calculate this capacitance is the question. We know that in the resonating circuit XL and XC are equal. XL is given, inductive impedance is 60, so XL is 60. What does it mean? XC must be also 60, because in oscillating circuit or series oscillating circuit or parallel, it doesn't matter. XL and XC are equal, so XC must be equal to 60 ohm. To get the capacitance, I am going to use this capacitive impedance equation. Xc is equal to 1 over 2 pi f c. Because I will calculate c, I will exchange cross product xc and c. Then my equation will change to c is equal to 1 over 2 pi f xc. After that, insert the numbers. 1 over 2 pi is 6.28. F is given in the question as, I think, 60 Hertz. Xc is equal to XL, which is 60 ohm. After that, use your calculator. 1 divided by bracket 6.28 times 60 times 63,600, close the bracket. Answer is 4.4 times 10 to the power negative 5 farad, but microfarad multiplied by 10 to the power of 6 times 4.4 times 10 to the power of negative 5 farad, but we converted microfarad, it becomes 44 microfarad. So A is the correct answer. Question number 13. An AC source is connected across a series combination of inductive coil with a specified resistance, so it is not a pure resistor, a pure coil as you see. And also inductive impedance, yani XL of the coil is given, XL of the coil is given, and capacitance of the capacity, C for the capacitor is given, 94 microfarad. To reach resonance, we know the condition for resonance, XC and XL must be equal. Finding resonance frequency, F is the question. Because C is given, I can use this equation X, because XL and XC equal to, and XL is given as 65, XC also must be equal to 65 ohm. Equation for XC is 1 over 2 pi f c, which is equal to 65. I will calculate F, so let me take F instead of 65, and let 65 take in here. So F becomes 1 over 2 pi. 2 pi is 6.28. So C 65, which is equal to XL in resonating circuit, multiplied by CC is given as 49 microfarad. I have to convert it to farad by multiplying 10 to the power negative 6. So let's get the answer. 1 divided by bracket 6.28 times 65 times 49 times 10 to the power of negative 6. Answer is almost 50 Hertz. Yeah, F is equal to 50 Hertz. And question number 14. A resonance circuit is made up of an inductive coil and a variable capacitor. If the capacitance of the capacitor is lowered from 1000 microfarad to 250 microfarad, by which factor the frequency of the circuit changes? So it changes from 1000 to 250. So if you say 1000 is C, 250 will be C over 4, because if we divide 1000 by 4, we got 250. And we know that as capacitance decreases, frequency increases. Capacitance decreases by 4, as you see, but frequency must increase not by 4, root of 4, because there's a root in the equation. Root of 4 is equal to 2. You can go that way. And also mathematically, we know that F is inversely proportional to root of C. Only you should write instead of C, root of C over 4, 1 over C over 4. So this 4 must be flipped to the numerator. Root of 4 must be flipped to numerator. When it's flipped to numerator, it becomes root of 4 divided by root of C. And as you see, the first term is multiplied by root of 4. How much is root of 4? It is 2. That's why frequency also must be multiplied by 2. So it must change to 2F. So B is the correct answer. For an AC series resonance circuit contains L, R, C, which of the following is correct? For our LC resonating circuit, it doesn't matter R exists or not. So LC are in resonance. That's why equation for frequency is going to be A. B is nothing, C is nothing, D is nothing. So A is correct answer. So this is all about our LC parallel and resonating circuits.